Thanks for the nice introduction. It is my great pleasure and honor to present a mini keynote in the data exploration session at SIGMOD 2021. Today, I will be talking about natural language-based exploration with relational databases in Chatbot. We clearly see that virtually every database will be on cloud. So, all database vendors strive to survive in this market. In an era of cloud computing, everybody wants to use database like your TV. However, learning SQL is difficult for ordinary users. Natural language interfaces make human to interact with DBMSs through the use of natural language. Chatbots are the most popular way to interact with the people. A chatbot is essentially a robot we can chat or interact with online via text or text-to-speech. There are diverse chatbots in many domains. Examples include Google Assistant, a more general-purpose chatbot, HIC, a website creation chatbot, Amtrak, a railway passenger service chatbot. Thus, data exploration with ordinary people could be possible with special chatbots. Now, Hyuk-kyu, one of my PhD students, is going to demonstrate SQLbot, a special chatbot for enabling exploration with relational databases. Okay, this is the initial page for SQLbot being developed by our lab at PostTech. You see the first instruction by SQLbot. Please select a database. Now you can select a database in the first pull-down menu on the left. I chose the Employee Hire Evaluation database. Then SQLbot shows the schema information in a graphical format for the chosen database. This database consists of 4 tables: evaluation, employee, hiring, and the shop. The shop and employees tables contain information about shops and employees hired by those shops. The hiring table contains hiring information between shops and employees. The evaluation table shows evaluation information about employees. Now let's find how many employees in the employee table.
How many employees are there?
Let's send a group by query in natural language.
How many stores are there in each location?
SQLbot then returns result in a histogram format. Now let's send an order by query in natural language.
Sort all the stores by number products in descending order and return the name and location and district of each store.
SQLbot then returns ordered result in a table format. Now let's find all the employees employed by shops. This requires a 3-table join query among the shop, employee, and hiring tables.
Show all store IDs and the names and ages of their employees.
Now let's send a query requiring set intersection.
Which store has both employees younger than 24 and employees older than 28?
Here, only shop 1 contains both employees younger than 24 and employees older than 20. Lastly, one can find the employee who got the highest one-time bonus using order by and limit clauses.
Find the name of the employee who got the highest one-time bonus.
As we saw in this demo using the toy database, simple relational data exploration is possible with the advanced of deep learning based techniques, especially in natural language processing and the database. As shown in this demo, there are three major functionalities in data exploration chatbot: natural language to SQL, NL to SQL. Here, the most important parts are an encoder and a decoder. An encoder in NL2SQL generates a deep representation from a pair of natural language question and a database schema, while a decoder generates an SQL query from the deep representation encoded. The second part is to visualize query results. This is a bit rule-based, since output formats and their value distribution can be captured from the SQL query and their values. Alternatively, one can give a natural language instruction on how to visualize the query results. The last part is to support conversational NL2SQL. Here, a dialogue history should be considered. Thus, in order to support a conversational functionality, we need to replace an encoder with a new one, which additionally takes a dialogue history. Due to time limit, I mostly focus on the first part in this talk. NL2SQL is to find an SQL statement to answer a natural language question on a database. For example, if a natural language question, how large is text, is given on the geography database, we can translate the question into the following SQL query. NL2SQL has been studied both in the database community and the natural language-based community since 1970s. Early techniques are rule-based methods, then use mappings and translation rules. Recently, many studies have been conducted by using the state-of-the-art deep learning models and algorithms. From the history of NL2SQL, we see that Chatbot AD was developed in 1982 by Pereira and Warren. This chatbot can answer questions on a special domain, geography. They mostly use manually built lexicon and grammar. RedSQL is the state-of-the-art in NL2SQL, although there are several variants which marginally outperforms it. Thus, I'd like to explain how RedSQL translates a natural language question into an SQL query. Here is a motivating example. Suppose that QNL is given for the cars with the 4 cylinders, which model has the largest horsepower. Here we assume that we have 3 tables in the database: cars data, models, and brand. Then correct SQL is shown here. This is join table between 2 tables, models and car data. Since we have to access the horsepower column in the cars data and the name column in models table. RedSQL considers 2 types of encodings: question encoding and schema encoding. The question encoding encodes a series of natural language tokens into their deep representations, or contextualized vectors. This is the same as typical encoding scheme, which is widely used in natural language processing. Schema encoding encodes a graph structure schema into deep representations. Unlike sentences, we have to consider the complex relationships between nodes in the schema graph. Redscale also considers schema linking in the encoding, which enables the model to align column or table references in the question to the corresponding schema columns and tables. This information captures latent linking between question and the table or columns. So in this example, Redscale considers three types of linking: question token to column, and the question token to table name, and the value to column name. Redscale exploits transformer to encode the input vectors. Suppose that input is a series of tokens. Then transformer generates their deep representation, which are also called the contextualized vectors. Here, the transformer consists of a stack of self-potential layers. In the next slide, I will explain the concept called self-attention a bit more. Self-attention computes around the relation between all the input elements, and the strength of this relation is encoded in the attention scores. The attention score is interpreted as a relative similarity between two elements. More specifically, given each token xi, we first generate three embeddings qi, ki, vi. Then the attention score alpha ij between every pair of qi and kj is computed here as a relative similarity. Next, we generate a contextualized output vector using the weighted sum of all input vectors using the attention scores computed. In order to effectively bias the transformer toward the arbitrary relational information in the question and the schema, Redscale uses relation-aware self-attention, which leverages learned relative positional embeddings beta ij and epsilon ij when computing alpha ij and yi. Here, as the similarity between qi and kj decreases, their attention score gets smaller. That is, this relation-aware self-attention is biased towards relations using these relative positional embeddings. Relational-aware self-attention in the transformer allows encoding arbitrary relations between question words and schema elements explicitly. And these representations are computed jointly over all input tokens. That is, question encoding, schema encoding, and schema linking can be done at the same time with the relation-aware self-attention. Now I explain how each element in the schema computes a contextualized vector that is a deep representation of the element. Suppose that we generate the contextualized vector for car ID. So when we compute the attention score between car ID and the model name, their relationship is more important than the one between car ID and horsepower, since name and car ID are in the same table. Similarly, schema linking can be done using predefined linking relations. Here, Redscale uses two types of schema linking: name-based linking and value-based linking. Name-based linking refers to exact or partial occurrences of column or table names in the question, such as the occurrences of cylinder and cars in the question. While value-based linking refers to occurrences of question to schema alignment, where the question mentions any values that occur in the database and consequently participate in the desired SQL. This example shows how relation-aware transformer performed three tasks: question encoding, and the schema encoding, and the schema linking. For example, when we encode cars data table, we encode partial name-based linking, and the foreign key table information and primary key information and the column members information as well. Now I'd like to talk about how an NL2 SQL decodes deep representations into an output SQL query. Here we explain a grammar-based decoder which is used in IRNet. RedSQL also uses a similar grammar-based decoder to this one. Here the decoder uses a simplified query language called SAMQL rather than using full SQL grammar. You can see the part of a SAMQL grammar and the derivation tree for a SAMQL query. The grammar-based decoder exploits LSTM to model the generation process of a query via sequential applications of actions. Here, each action chooses a production rule to apply to the current derivation tree of a query. The decoder LSTM chooses a series of production rules to generate a derivation tree. The chosen rules are colored in blue. First, the decoder chooses this rule and feeds this information into a decoder LSTM. Here we choose this production rule, select equals distinct and aggregations. In the next step, we need to predict whether this query requires distinct keyword in the select clause. Here, the decoder chooses the second rule, indicating that this query does not need a distinct keyword in the select clause. Similarly, we can decode all the remaining parts in the derivation tree. Here, the most important part in conversational NSQL is how to capture the context during dialogue. For example, consider the first two questions. How many dorms have a TV lounge? And what is the total capacity of these dorms? Here we need to understand what these dorms are, which is the most important context in the translation. Now I briefly explain how we can extend the NL2 SQL to support dialogue based on NL2 SQL. That is conversational NL2 SQL. Okay. The state-of-the-art in conversational NL2 SQL exploits a pre-trained model called SCORE rather than using general language models. The pre-training is on top of Roberta and uses the three additional loss functions to inject the context-related inductive bias into language models. SCORE extensively uses synthetically generated data in the pre-training. And SCORE is regarded as a pre-training model, which jointly represents the natural language question and the underlying database schema, while taking into consideration the multi-turn dynamics of dialogue to capture the context information. Then the encoder of RedSQL additionally takes dialogue history to understand the context of dialogue. So far, I have talked about the state of art in NL2SQL and the conversational NL2SQL to develop a data exploration chatbot. Here are some research challenges. One serious problem in NL2SQL is the absence of a semantic equivalence checking tool. That is, we need to check if the predictive query is semantically equivalent to a gold query. On the other hand, existing approaches use query results-based equivalence or syntactic level equivalence, which leads to significant inaccuracy. Although Cosetta guarantees the semantic equivalence between two queries, its coverage is quite limited. In our VLDB paper, we proposed the multi-level validation tool by exploiting the following three techniques. First, exploiting Cosetta as a filter. And then we apply query rewrite and check semantic equivalence, actually syntactic equivalence between two redundant queries.
And then we apply the query execution with the various database instances generated by database testing techniques. However, our tool still incurs false positives. So this calls for a new tool to formally check semantic equivalence between two queries. Despite the high accuracy of the state-of-the-art NL2 SQL system, one may wonder whether RedSQL can accurately translate queries in Chatbot. We tested 6 queries from the VLDB 1981 paper, from Q1 to Q6. This slide shows a query generated by RedSQL and Bold query. RedSQL does not correctly translate this NL question since it fails to isolate independent parts of a complex natural language question, which employs aged over 40 on the first floor on more than their majors. So here, employee tables are referenced twice in the nested query. However, if you look at the predictive one, employee table is referenced once. So this is a little bit difficult for RedSQL. Now let's see the predictive query for Q4. What are the countries bordering the Soviet Union whose population exceeds the population of the United Kingdom? This also involves the complex join relationships and the nested query. So RedSQL does not correctly translate this query. This slide shows query results for Q5. Which American countries do not border the Pacific? Actually, this query involves negation plus complex joins. If you look at the Bold query, it utilizes not in. Also, the predictive one also utilizes not in. However, this complex join relationship is not captured in predictive. This slide shows query result for Q6. Which countries border exactly 2 Cs? And Q6 requires group by and having clauses in a predictive query. But if you look at predictive one, it does not have a group by and having clauses. Here is a summary of a result by RedSQL plus BERT. Surprisingly, the state-of-the-art NL2 SQL system does not correctly translate any query used in the VLDB 1981. The coverage of the SOTA system is quite limited. The following expressions are very difficult to translate. Complex join conditions plus nested queries, and complex group by and having clauses. To conclude, natural language-based data exploration has a high potential due to the advance of deep learning techniques. Still, there are many issues which hinder deployment of data exploration chatbot for real-world databases. In this talk, I listed some of challenges that should be addressed in the near future. Thanks for your attention.